and welcome back to Stoichiometry Review Guide. This is part 5, pages 8 through 12. We are looking at empirical and molecular formulae. So to start off, looking just at empirical formulae, this is easy going from molecular to empirical. Because you know the definition of empirical formula is simply that lowest whole number ratio of all of the subscripts in the formula. So if we're looking at C2H6, I figure out what is the greatest common factor between 2 and 6. That would be 2. Divide both of those subscripts by 2. 2 divided by 2 is 1. 6 divided by 2 is 3. So our empirical formula, C1H3, and of course you don't have to draw the 1, so CH3 would also be a good answer. 4 and 8, we can divide those both by 4. So we get C1H2 or simply CH2. 6, 12, and 6, I can divide everything by 6. And we end up with C1H2O1. 2 and 4, I can divide those both by 2. We end up with C1H2. 1 and 4, I can only divide those by 1. So here, the empirical formula is the same as the molecular formula. N2O2, I can divide those both by 2, and I get N1O1, or simply NO. Good? Great. So things get a little bit more difficult when we're given grams or percent of elements in a compound. Our step is probably not a surprise, convert to moles first. And then we're going to take the decimal moles that we get and divide by the smallest. Divide by the smallest of all those subscripts to get rid of the decimals. And then we're going to be somewhat liberal in rounding, so 2.99 would be 3. But if I had like 1 to 2.5, do not round 0.5. Instead, scale those both up by 2. So instead of 1 to 2.5, you'd get 2 to 5. And if you had like 1 to 1 1/3, multiply by 3 and get a ratio of 3 to 4. Good? Good. So hopefully you have your calculators and periodic tables ready, because here we go. I've got 94.07 grams of sulfur, 5.93 grams of hydrogen. So step 1 is always to convert those to moles first. Looking at our handy-dandy periodic table, sulfur has a mass of 32.066. Per mole. Same thing for hydrogen, 5.93 grams of hydrogen. Divide by the molar mass. Grams cancels out, grams cancels out. We do those calculations, 94.07 times 1 divided by 32.066 gives us 2.93 moles of sulfur. 5.93 times 1 divided by 1.008 gives us 5.88 moles of hydrogen. So I could take these mole numbers and write my formula, but no one loves all those decimals, and so we're going to divide by the smallest of all our subscripts, and in this case it's 2.93. 2.93 divided by 2.93 gives us 1, and 5.88 divided by 2.93 gives us 2. So this is our empirical formula, and of course you don't have to write the 1. So if that makes you happier, that is also a correct answer. Good? Let's do another one. Empirical formula, we have grams of iron, sulfur, and oxygen. We're going to do the same thing. Turn our grams of iron into moles. turn our grams of sulfur into moles. I'm going to put oxygen over here. I'm running out of space. Turn our grams of oxygen into moles. Molar mass of iron, according to the periodic table, is 55.845. That sulfur is still 32.066. And oxygen, of course, is 15.999. So that iron is going to be 55.845 grams per 1 mole. And sulfur, 32.066 grams per 1 mole. And oxygen, 15.999 grams per 1 mole. Grams top and bottom cancel out in each and every one of these elements. And then we get some mole numbers. So for iron, we end up with a lot of zeros. And here, a lot more zeros. And once again, a bunch of zeros. Next step, divide by the smallest, 0002 bunch of stuff, 0007 bunch of stuff. 2 is smaller. So we're going to divide everything by that same smallest number. And so here we get 1, and here we get 1, and here we get 3. So our formula, our empirical formula, is going to be Fe1S1O3 or FeSO3. Let's do another practice problem. So this one is a little bit different. Instead of being given grams, we've been given our percent composition. All we're going to do is pretend like we have 100 grams. And so if I have 100 grams, 80.68% of that mercury will be 80.68 grams of mercury, and do the same thing over and over. So let's go ahead and do that problem. Empirical formula, when we have percents of mercury, oxygen, and sulfur, we're simply going to assume that we have 100 grams. So 80.68% of 100 grams is 80.68 grams of mercury. And I'm going to turn that into moles of mercury by looking at the mass on the periodic table. Mercury is way down here, 200.59. Oops. 200.59 grams per mole. Same thing for oxygen. So that 12.87% of 100 turns into 12.78 grams of oxygen. Turn those into moles, 15.999 grams in 1 mole of oxygen. And then last but not least, 6.45% sulfur. 6.45% of 100 is 6.45 grams of sulfur. And we know from our periodic table that the mass of sulfur is 32.066 grams per mole. Notice that grams cancel out in each and every problem. So now I can do that division. 80.68 divided by 200.59 gives us 0.4022 moles of mercury. 12.87 divided by 15.999 gives us 0.8044 moles of oxygen. And 6.45 divided by 32.066 gives us 0.2011 moles of sulfur. I look at my 3. I'm going to choose the smallest of the 3 and divide everything by the smallest. 0.2011 is the smallest, so I divide everything by 0.2011. 0.4022 divided by 0.2011, I can actually do that in my head. It's 2. Here we have 4. Here we have 1. So then our formula becomes Hg2O4S1. I actually don't like to put the S before the O. This is correct, but I like that better. But this would also be correct. Good? Good. Let's do a couple more. So we have a compound that is 32.8% chromium and the rest is chlorine. The rest is chlorine. I don't have a number. How do I figure out the rest? Well, remember that percent is always out of 100. So the rest being chlorine is going to be 100 minus the 32.8% that is chromium, which is going to give us 67.2% chlorine. We're going to choose to have 100 grams. So 32.8% of 100 grams is 32.8 grams of chromium. Find chromium on the periodic table. Chromium is right here by manganese, 51.996. Grams per mole. Same thing for chlorine. We have 67.2%. 67.2% of 100 is 67.2 grams of chlorine. Find chlorine on the periodic table. The mass is 35.453 grams per mole. Do these divisions. 32.8 divided by 51.996 gives us 0.631 moles of chromium, and 67.2 divided by 35.453 gives us 1.895 moles of chlorine. Next step, divide by the smallest. The smallest in this case is 0.631. So we're going to divide everything by 0.631. And I get 1 chromium and 3 chlorines. So our empirical formula, CrCl3. Next one, 300 grams. Who even cares? I have percents. I'm going to pick 100. So we have carbon, hydrogen, oxygen. If hydrogen is 5.98823, that's a lot of sig figs. And then carbon and oxygen are the same. We're going to have to do a little bit of algebra. So you know that all 3 of these are going to add up to 100. If I do 100 minus that 5.98823, we end up with 94.01177. But this is equally carbon and oxygen. So I'm going to divide that by 2. And we get, oh my gosh, so many digits, 47.005885. This is going to be our percent carbon and oxygen. So let's go ahead and start with our carbon first. 47.005885 grams of carbon. And if you don't want to work with 100, if you want to keep that 300, you totally can. You would just take that 47, multiply it by 300, and then you get 140 something. But that's more work than you have to do. So my recommendation is that you skip through 300. If you have percents, always work with 100. So anyhow, 47.005885 carbons, 12.011 grams per mole of carbon. Let's do our hydrogen next. 5.98823 grams of hydrogen, 1.008 grams per mole of hydrogen. And then oxygen, 47.005885 grams of oxygen divided by, oh dear, I can't write any lower on my screen. We're going to go sideways. 15.999 grams per mole of oxygen. All right, so then we end up with 3.914 moles of carbon and 5.941 moles of hydrogen. And here 2.938 moles of oxygen. Divide everything by the smallest number. That would be our oxygen, 2.938, 2.938, 2.938. And we end up with carbon 2. Oops, hydrogen 2. Ignore that. Carbon is 1.33. Hydrogen is 2, and oxygen is 1. Can I round away this 0.33? I really shouldn't. That's a lot of rounding. So instead, we're going to scale the whole thing up to get rid of 0.33, which is the same as a third. We're going to multiply everything by 3. So 3 times 1 1/3 is going to be 4. 3 times 2 is 6, and 3 times 1 is 3. This is our empirical formula. How about this guy? I've got some potassium, some carbon, and some oxygen. I'm going to have to turn my grams into moles. Or do I? Look what we're given. We already have moles. We already have moles. Do I have to turn my grams into moles? No. Do I need to turn my moles into grams? No, because if we look back here, it's all about the mole. So this question is actually easier than anything that we've done so far in this video. Well, okay, maybe not the original empirical formula stuff, but this is the easiest one that we've done on this page. So I don't have to turn my grams into moles. I already have moles. So I have 0.104 potassiums, 0.052 carbons, and 0.156 oxygens. Still going to divide by the smallest of the 3, which in this case is 0.052. Potassium becomes 2, carbon is 1, and oxygen is 3. This is my empirical formula, K2C1O3. Easy peasy. That's our empirical formula. Next video is going to be how to turn empirical formulae into molecular formulae. But for now, this is all we've got.